Good morning and welcome once again to Florida Aviation Network's productions of Plane Time. This one is number 26, broadcasting live from the Gizmo Studios in Oviedo, Florida. Today's presentations are themed on the gliding community, so if you're a gliding enthusiast or want to become one, tune in, sit back with a cup of joe, and enjoy our first presentation today on Soaring Weather. We have with us in the studio today a veteran of many broadcasts with the Florida Aviation Network, Dr. George Bartuska. George is our science officer and weather guy. George, welcome back once again.
Thanks. Hello, everyone. Let me say up front that we have a lot of material to get through, and so I'm going to skip a couple slides, but this is a very unique soaring weather is a very unique topic compared to powered flight weather. Excuse me. In weather for glider pilots, the saying is we need calm, steady winds and rising air. But what's the meteorology behind that? Well, the meteorology is the physics, and normally I would cover this in one semester, and I've got about 20 to 25 minutes, so here we go. In a regular class, I'd be covering all these things, but we're just going to hit the unique things. I want to make you aware of this glider flying handbook by the FAA, which was put out in 2024, updated. Some of the material I'm going to show today is directly from that. Now, since we're normally talking to powered flight pilots, I want to just talk a little bit about gliding first. So a glider is a non-powered, heavier than air aircraft. Meteorology is a very critical factor in planning. In fact, when a glider pilot's getting ready to glide, they should be looking at the weather days ahead to get an idea what it's going to be. Soaring can be challenging and rewarding. Thermal soaring, sea breeze soaring, hill soaring, and mountain wave soaring are the kind of things we're going to talk about today. You should be aware that you may need supplemental oxygen when you're soaring, and there are multiple launch methods. Now, let's compare a glider to a powered flight. Typically, gliders have no engines, rely on air currents to stay aloft. Gliders glide, power aircraft generate thrust. The unique thing about a glider, as you can tell by these pictures, they have narrow wing design to maximize lift. A glider is always sinking at some rate to stay aloft, even when it's in a thermal. Gliders are going to require to be towed either by an aircraft or by a winch to get aloft, and once again, supplemental oxygen may be necessary. Okay, I said gliders don't normally have an engine, but glider can have an engine. There's a unique one at the top there, design, and some gliders have supplemental power of various sources to fly. Now, one of the advantages of a glider, there's no worry about engine out on landing. There's no worry about a cockpit fire, but you could have a tow rope break during launch, so you got to be aware. Now, one of the things I want to point out that a lot of people don't know, the Wright brothers, yes, the American inventors, aviation pioneers who achieved the first powered, sustained, and controlled airplane flight, but everything they did to prove what they found out was done with a glider. They made approximately 3 gliders that they destroyed and broke at Kitty Hawk, but it was once they perfected the wing warping with the glider that they went to the point of actually going to powered flight. Now, pilots need to know a certain amount of things when they go fly. They need to know the wind direction and the wind velocity at the ground level. They need to know the visibility. They need to know temperature and dew point, atmospheric pressure for their altimeter setting, levels where clouds can be encountered, and we're going to talk about that later. Sky areas where there might be severe turbulence or bumpiness, levels where there might be ice formation if you're going to go that high, and conditions expected at the flight destination if you're not coming right back to where you took off. What do glider pilots need to know? The same thing and more. Now, soaring relies on rising air currents to stay aloft. There are 4 main sources of that. The first one we call orographic lifting, where a hill or a mountain is going to cause the air to rise. The second kind is frontal wedging. Usually that's only comes into play if you're a very experienced glider and you're going to use a cold front. I have pictured here a warm front, but a cold front can provide lifting action, but it can also be very dangerous. Sea breeze soaring or convergence we're going to talk about, and then just regular thermals. Now, the source of energy normally from the meteorological standpoint is the sun. The sun gives us all the energy we need for weather. There is another source of energy for thermals, and that is heat islands from large cities, but today we're just talking about the weather part. Now, the wavelength matters. Here we have a diagram showing radiation from the fire, like comes from the sun, conduction when you actually have contact with a heat source, and convection. In this case, we're boiling water. In the atmosphere, we're boiling air, so to speak. Like I said, wavelength matters. The sun barely heats the atmosphere. Most of the sun rays, because they're at the wrong wavelength, go right through the atmosphere and then heat the ground. So our tropopause, our troposphere is heated from the bottom up, which is good for glider pilots because that's what they want. They want something that's rising. So radiation heats the ground, and because the air is in contact with the earth, we have conduction, and that starts convection. As the air gets warmer, it becomes less dense and it will rise. Now we're going to start out by talking about regular thermals. A thermal can be described as a column or a plume when it rises in a relatively steady vertical stream of air. In addition to these constant rising things, we have bubbles, which is kind of like the partial when we talk about partial meteorology. Here's a diagram that shows a typical situation where a glider pilot is taking advantage of a thermal. The thermals on the left is being generated over a plowed field, which is a good source. And you can see on the right-hand side where there could be heat off a major city, off a hotspot. But once they've gotten up near the bottom of the cloud, they're going to get away from that and go find another thermal, because you did not want to get sucked into the cloud if it's on its way to becoming a thunderstorm. Here are the stages of thunderstorm development. We have cumulus, we have mature, and we have dissipating. Glider pilots love the cumulus stage because the only way you can get a cumulus cloud is you must have rising air, and that's what they're looking for. Now here's what a plume looks like in a diagram. Notice we have air going up in the middle, but we have air coming down on the outside with some eddies. So we have to stay within a small circle when we're taking advantage of that. Those bubbles we talked about, once again, if you stay in the bubble, there'll be some air, but once you get out of the bubble, there won't be any air. There are times, in this case, where bubbles form and then another bubble forms, so it's out there and we're looking for it. The other thing that happens are vortex rings. This is the only illustration I could find of a vortex ring. It happens to do with a downdraft or a microburst. Just flip that around and think in your head that the air is moving up. It has the same potential to create that vortex ring. Here's a cross section through a thermal, and here's a summary again of a pilot utilizing a thermal. In soaring, we're concerned about why clouds develop, what form they'll take and what they'll look like and when they'll go away. It's this process of condensation that creates the cloud, and I'm going to talk about that in the middle. This is pretty wordy. You'll be able to look at this again later. I just want that last sentence. Typically, the earliest time soaring can start is just before noon and early afternoon, depending on the solar weather state, because there won't be enough energy in the morning or later in the day to create a thermal. Now, if you've seen me before, I say water is the dynamite of weather everywhere on Earth. Even if we have sun, we're not going to have any weather or clouds or severe weather unless there's water vapor in the air. Everyone's been swimming, and you know when you get out of the water, whether it's a beach or a pool, you feel cold, even if the water's warm or if the air's warm. Why? Because evaporation is taking place, and evaporation is a cooling process. The water is sucking the heat out of your body to change from a liquid to a gas. Well, the same thing happens in reverse during condensation. When the air is cooled to its dew point, the water comes back out of the air and it gives off heat. Okay? In these two kinds of heat transfer, the one on the left is the one I'm going to talk about. Latent heat transfer is a process without the change of a body's temperature, i.e. either evaporative cooling or condensation heating. You can see here in this diagram that condensation and evaporation are opposites. Now I want to give an example of this cloud formation. Here we're going to talk about fog. This was Interstate 4 in Central Florida, January 9, 2008. Interstate 4, about 70 vehicles crashed into each other, 4 people died, 38 injured, 5 seriously. This is the weather map that existed on that day. I'm going to do a close-up in a minute, but I want to review the station model on a surface weather map. We're concerned with the temperature at 57 degrees. It's always the upper left-hand number, and the dew point is always the lower left-hand number. And when the temperature and the dew point spread is less than 5 degrees Fahrenheit or 3 degrees Celsius, we're going to have fog, or we're going to have a cloud, or we're going to have rain. Unlike relative humidity, dew point's a measure of the actual water vapor in the air. This is the temperature to which air must be cooled in order to become saturated and therefore reach 100% relative humidity. Now we're going to zero in on that map on that day. In this map in the middle of the state of Florida, you can see a number 214, and that relates to the barometric pressure at the time. But above it is the station for Orlando. You see the temperature is 53 degrees, the dew point is 53 degrees. They're not only within 5 degrees of each other, they're exactly the same temperature. Go north to Jacksonville, we can see the temperature and the dew point were both 56. Jump over to Tallahassee, we can see they were both 57. And in offshore Bowie, they were 70 and 71. So I've drawn a little circle there of where we would have known there was fog or cloudiness. So this stuff can be predicted. How do we do it? We do it with a sling psychrometer. A sling psychrometer has 2 thermometers mounted side by side, one with a wick that we can put water on it. And the idea, remember when you get out of the pool, the water starts to evaporate from your heat. We take this sling psychrometer, let me back up to the other picture, and we sling it around. We whip it around. If you can put the camera, there we go. Here's how we use a sling psychrometer. It's called a sling psychrometer because we're slinging it. And as we do, if the relative humidity was 100%, both thermometers would read the same temperature. But if it's not 100%, the one with the wick is going to read a lower temperature. And by using the chart on the instrument or your handheld phone, you can dial in a computer and look at that. So once again, when the temperature dew point spread is less than 5 degrees Fahrenheit or 3 degrees centigrade Celsius, there's going to be fog or a cloud. Now, at this point in a regular presentation in a classroom, I'd go into the atmospheric thermodynamics, talking about skew-T diagrams and wet and dry adiabatic cooling and heating. We don't have time for that today, so I'm going to give you the generic version of what this is all about. That car on the left, that dark car, is our car. This is at Daytona Beach. We get out, we throw our towels in the car, we go out swimming for an hour or two. When we come back and we open the door of that car. Now it's been sitting there for an hour, so it's probably close to 180 degrees inside. When we open the door of that car, a bubble of hot air comes out, and it acts just like a hot air balloon, and it starts to rise. And as it rises, it expands, and as it expands, it cools. And you notice in that picture there's no clouds in the sky, so let's just say for conversation's sake it goes up to about 5,000 feet. And it's now equalized with the temperature around it. It doesn't have any water vapor on it, and boop, that's it. Nothing happens. Now, we dry off our towels. We get our towels all wet. If you're on Daytona in the summer, you know there's a hot dog truck either direction. We throw our wet towels back in the car, lock up the car, and we go down and get a hot dog and a soda. While we're there, we meet some friends, and an hour goes by. We come back to that car. We open it up again. This time, yeah, it's 180 degrees again, but that bubble that comes out is saturated. That air has been saturated from the water from the towels. Now it's going to rise again a little bit slower, and it's going to expand, and it's going to cool. But this time, when it gets up to around 5,000 feet, let's say, the water is going to cool to the dew point, and as it cools to the dew point, a cloud is going to start to form, and it's going to give off heat. And as it gives off heat, it's going to start going faster and faster above us. That's what a thermal is. That's the meteorology behind a thermal. So what are those levels? That condensation level is called the LCL, the lifted condensation level. And assuming there's no inversion in the atmosphere, when it reaches a point where the air, where it's giving off enough heat from the condensation, it'll start going. It can get going up to 60 miles an hour, and it'll go until it runs out of water vapor at the equalization level. For those of you who have a little science background, these again are the levels. The level of lifted condensation level is basically the cloud base, the level of free convection is where it takes off, and the equalization level is where it stops rising. Okay, now we're going to put all that into effect. Florida is a unique place on planet Earth. It's the only place where there's a peninsula that has water on both sides, the Gulf on one side and the North Atlantic on the other. When the sun heats, remember I told you the sun barely heats the atmosphere. So it heats the land and it heats the water. But the land has very low heat capacity. So the minute it heats up the land starts giving that heat back off, and it starts a rising current, a thermal. And as it does, it's going to pull air in off the water and create a sea breeze. The unique thing here in Florida is it creates dual sea breezes, one for each coast. And as a result, we get this airflow situation coming off both coasts. And if there were no other weather systems in Florida, we'd have thunderstorms right up and down the middle of the state every day in the summer. But we do have other weather systems. We have high pressures, low pressures, and frontal boundaries. Now, the thing to remember is, as a glider pilot, we don't want to end up in a thunderstorm. So we simply need to be aware of this, and when we start to see the cumulus cloud growing into a mature or a cumulonimbus, we want to be moving on to somewhere else. Now, the next thing I want to talk is the mountains or hills. Flying at elevated altitudes can rob an aircraft of more than half its sea level rated performance. So keep that in mind no matter what you're flying. This is the situation that takes place around mountains. We have what we call waves. Some people call these mountain waves, gravity waves, and they end up being very good places for glider pilots to fly. But remember, mountains are physical barriers that force the local winds to change course. They either make the air speed up, slow down, rise, or sink on the other side. Mountain soaring can be hazardous from vertical and rotor-type currents occurring on the leeward side of the ridge, the other side. Mountains can establish standing waves that can develop into a series of wave downstream of the ridge. They can go down for a couple hundred miles. While standing waves can remain mostly stationary, strong winds can go through them. Airflow can dip sharply. We're going to see this in the next one. Most U.S. mountain ranges are oriented north and south, while the prevailing winds are usually from the west. This causes winds to rise over the mountain ranges, which is a good place to pick up a rising air for a glider. However, it's going to go down on the opposite side. On these ranges, the west side is the upslope or the windward side, whereas on the east side is the downslope or the leeward side. Here's a really good example of that. Notice as the air is rising again, we're going to get condensation and we're going to get clouds. And right there where it says the air expanding, that's where you're going to find thermals and rising air to fly your glider, not on the other side. And we want to just make mention, when you're thinking about air going over a mountain, think about water in a stream going around boulders. Upwind slopes, updrafts tend to be relatively stable and smooth, whereas the downward slopes, downdrafts tend to be more random and turbulent. This is an exception to all that, and I put this in here because of the Santa Ana winds in California in January when we had all those fires. All the wind was going the other way because it was a result of a high and low pressure zone. Turbulence is the thing we don't want to get involved in. Notice here when air is flowing around a mountain, on the leeward side, on the windward side, everything is nice, but on the other side, we start to get turbulence. If there's a channel or a groove in the mountain, the air can be sped up due to a Venturi effect. But here you can see when mountains going through the passes, you want to be on the right side or the rising air side. You don't want to be on the left side. Here's another review of that. Out in the mountains, we get these stationary lens-shaped clouds called lenticular clouds. They don't move, but there's definitely air moving underneath them. They form when stable air moves across the mountains and hills at different heights the same direction as strong air current. The cloud base is usually 6,500 to 16,500 foot. Associated with mountain wave turbulence is strong, gusty winds. And the rotor cloud, which I'm going to show here in a minute. You can see below here, let me back up a minute. When air flows over mountains, we get standing waves. I already talked about that. You can see how we now get a wave that's going up and down past the mountain, and they call that the hydraulic jump. They take that term from water hydraulics because at a dam or a water control structure, we'll get this hydraulic jump where the water's going from supercritical to subcritical. It's going from fast to slow. That's where this analogy comes. But notice in this picture we have a rotor. And that is the dangerous part about flying a glider in the vicinity of these. That rotor is not only dangerous to powered flight and helicopters, it's very dangerous to gliders. And remember, this is specifically important with your tow plane. Let's say you're in Denver, but at sea level, that plane may be able to take off in 830 feet. But in Denver at 6,000 feet, it's going to need 1,500 feet to take off because of the high density altitude. And you should know the high density or the density altitude criteria for your glider. The VFR regulations for glider are similar to flying a plane. We talked about supplemental oxygen at or below 14,000 feet for 30 minutes. You should have some kind of supplemental oxygen. Most gliders are not going to go that high, but if you plan to, you need to have that. Now let's talk a little bit about forecasting. A soaring forecast attempts to gauge the potential for atmosphere to provide thermal lifting mechanisms for gliders. A more unstable air mass, both in the low levels and aloft, is preferred to produce these thermals. But remember, they can create thunderstorms too. A forecast product issued by many, but not all National Weather Service offices, uses indices, and I'm going to talk about the lifted index in a minute. Most soundings are produced by the National Weather Service, but private sources may also be used. The data is collected at 12 UTC, usually serves as the input to the forecast. Now, the National Weather Service, TAFs, terminal aerodrome forecasts are issued 4 times a day at 0, 6, 12, and 18 Zulu, issued by the local weather forecast. They're going to give you the wind speed, the visibility, the present weather, such as fog or thunderstorms, cloud cover and heights, and low-level wind shear. Here's a plot from the Storm Prediction Center. I encourage you, this should be the first thing you always pull up to see what's happening where you're going to go gliding. The next thing at the FAA Aviation Weather Service, you can get the observation, you can get the terminal aerodrome forecast, and you can get warning about icing if you think you're going to be in an area where there might be icing. Now there's plenty of private services available, such as SkySight, XC Skies, and MeteoBlue. But in addition, the National Weather Service issues this lifted index for soaring, indicates the level of atmospheric instability. Instability means the ability to rise, for air to rise when it's ready to rise. With more negative values signifying better conditions for soaring, because it means the air is more unstable. You can see here if an LI is 0, the air is stable. If it's -3, it's marginally unstable. If it's -6, it's moderately unstable. -6 to -9, very unstable. And the problem is, in the 6 to 9 range, you're probably talking about severe weather, and that's probably not somewhere you want to be at that time. Here's a plot of what those LI looks like. The other thing you want to be aware of is that the National Weather Service issues special bulletins throughout the year just for glider pilots, and this is one, and I've got the address up there if you want to look it up. So that's been a very quick review of all the parts that can evolve for meteorology as applied to glider pilots. Remember, I didn't have time to do a whole semester here. I hit the hot points. Don't forget that book that's 2024 put out by the National Weather Service. And we'll see you next time. And don't forget, after the credits, there's going to be a code for you to put in to get your wings credit.